We have started with the unit momentum and energy, and in last lecture we have seen the law of conservation of the linear momentum and angular momentum for a single particle. Okay, now we are going to see work energy relation. Suppose there is a block at position A, or say at position 1, and if I apply some amount of force on it, it is moving to the position 2. So the displacement of this block will be from position 1 to the position 2. F is a force applied. So whenever there is a displacement of any particle or any body from one position to another position on application of the external applied force, then work is done. So the work is defined by force into displacement. And therefore it can be given by F into S. Now according to the Newton's second law, we know that this F is equal to dp upon dt, which we have seen in the last lecture. And according to the kinematic equations, we also know that suppose let u is the initial velocity and if this v is a final velocity, we can write v square is equal to u square plus 2as. From this equation I can find out this equation for the s. So I can write s is equal to v square minus u square upon 2a. Now just let us put the value of this s into this equation. Another definition of the force is mass into acceleration. Therefore we can, now we have to put this value and not this value. Therefore w is equal to ma into this value of s, v square minus u square upon 2a 1 half m into v square minus 1 half m into u square. So this 1 half m into v square is nothing but the kinetic energy of this second position, because v is the final velocity. Therefore I can write it as a kinetic energy of this position 2 minus 1 half mu square, where u is the initial velocity, then 1 half mu square will be the kinetic energy of the first position. So this is 1. So I can write it as a T2 minus T1. So this is the relation between the work and the kinetic energy. Now let us see the law of conservation of energy. Law of conservation of the energy says that the energy can neither be created nor it can be destroyed, but it can be just converted from one form to the another form. Suppose for the same block, when this block is at rest, it is having only potential energy, and when we apply some amount of force on it, it will start moving from this position 1 to position 2. So all of its potential energy will be converted into the kinetic energy. Similarly, when it comes to the rest, or when it comes to the position 2, so all its kinetic energy will be again converted to the potential energy. In this event, we can see that the energy is not created, or it is not destroyed. It is just converting from one form to the another form. Okay, so this is called as a law of conservation of the energy. Now suppose this W, it can be given by F into dr. R is a very small displacement. Then the work done, W12, it is given by F into dr, where F is a force and dr is a small displacement. Now let me put the value of this F or For according to the Newton's second law, we know that F is equal to dp upon dt, and v is equal to dr upon dt. According to the definition of the velocity, it is the rate of change of displacement with respect to time. So I can write this dr as v dt. Now let us put these values in this equation. So I'm going to get W12 is equal to integration from 1 to 2 dp upon dt into v dt. So this dt will get cancelled, or let me just put the value of p as mv into v dt. So this v into v will become v square. So this m is constant, so it will come out of this integration. So we are going to get v square, and this dt will get cancelled. So from 1 to 2, so this is nothing but m upon 2, and it will be v2 minus v1. When we remove this integration, or when we solve this, we are going to get m by 2 v2 minus v1, or I can write v2 square minus v1 square. So I'm going to get 1/2 m v2 square minus 1/2 m v1 square. So 1/2 m v2 square is nothing but the kinetic energy of the final position, and 1/2 m v1 square is the kinetic energy of the first position. So I can write here ke2 minus ke1. So this is about the kinetic energy. This is the relation between the kinetic energy and this work function in some another form, or for very small portions. There is another form of a force which is given by F is equal to minus gamma into V. So this is a force in a form of the potential energy, where this V is a function of R. So if I put the value of this F into this equation, so W12 is equal to 1 to 2 minus gamma V into dr. So this delta is nothing but the gradient of the scalar potential, which we have studied in the first unit, which is gamma upon gamma x plus gamma into dx plus gamma v upon gamma y into dy plus gamma v upon gamma z into dz into this dr, integration from 1 to 2, which is nothing but a W12. And if I take this gradient of the scalar field, so it will become W12 is equal to, I'll write it directly here, so it will be V1 minus V2, or so if I solve this integration, so it will be V2 minus V1, and which will be nothing but V1 minus V2. So from this equation, let me call this as a equation 1, and this is nothing but the potential energy of a first position minus the potential energy of the second position. So let me call this as the equation number 2. So from equation 1 and 2, we can say that, so as equation 1 and equation 2 left hand side is equal, we can write it as a V1 minus V2 is equal to T2 minus T1. So this is T2 minus T1, or I can write V1 plus V1 plus T1 is equal to V2 plus T2. So we can say that the total energy, so the total energy is the potential energy plus kinetic energy for any system. So the potential energy and the kinetic energy or the total energy for the initial position and the total energy for the final position are same. It means that the energy is neither created nor it is lost. So this is a proof of the law of conservation of the energy.